Okay. I really hate to do this week because you're like also busy and focused on exam 1 and you care less about regression, but these are really important lectures. So today's lecture continues what we started last week on error discussion for the data, and it is very important. I hate to do it just before the exam, but I kind of have to, right? So I hope that you'll give it sufficient attention or come back to it on YouTube to kind of go through the material and conceptualize it again. All right, so last time we discussed the standard deviation as a measure of how the data is spread around the mean, okay? Now, just for the sake of the argument, I want to call the standard deviation an error, okay? I want to call it an error with respect to the mean. In other words, if you were to use the mean value, only the mean value, which is the simplest statistic you could use to describe a set of data, if you were to use the mean value to describe those data, then the error committed is the standard deviation. Okay, so that's the twist I want to pass on to you. Okay, and then you pass on to your kids and, you know, whoever you're teaching, is how to think about the standard deviation. Okay, as the error committed in your data if you were to use the mean value to describe those data. Okay, now you'll see where I'm headed with this. So this was the example we gave last time before you left off, and we said which one of those data has a larger standard deviation, a larger spread around the mean, and was this plot, this figure on the left. Okay, standard error. So now remember, we're doing regression, and regression was a methodology to develop a model to describe the trend in a set of data. So far, we've done only regression to a straight line, okay? But still, that's sufficient to discuss the error, or what type of errors are committed when doing that. We're gonna call that the standard error, but we're gonna repeat, the way I'm gonna describe it, I'm gonna repeat the same thing I did when discussing the mean value. So we're gonna consider the femur length and height data again with a linear regression, okay? With linear regression to a straight line, this blue line, okay? And recall that our model was a straight line, this A1x plus A0, okay? And as you can tell, just visually, that the regression line divides the data between values above it and values below it. This is called the spread of the data around the regression line. Previously, we had the spread of the data around the mean, okay? So now you can kind of foretell where I'm headed. Okay, and Maxime is like, has a grin on his face, like, I know where this is headed, maybe. I didn't mean to put you on the spot there, but I do appreciate the contribution. So anyway, so, you know, the data is spread around that regression line with data, some data points above it and some data points below it. Same thing we did with the mean value. Each one of those points lies at a distance yi minus fi from the regression line. Remember, yi is the value that was given to you, so that's that disk, that white disk with a black line around it, and the fi value is this one, is the is the predicted value by the regression line. So that distance, okay, that distance, we're going to use that distance to define an error, okay, just like we did with this with the mean value, okay? That's yi minus fi. All right. So now, same thing, exactly as we did with the mean, okay? The aggregate distance of all points from the mean, not the mean, this is a typo here. The aggregate distance of all points from the regression line, let me fix this right now, from the regression line, Okay, the average. Okay, so the average distance of all points from the regression line can be defined as the L2 norm of the distances yi minus fi squared. Now remember, when we were dealing with the mean, we had yi minus y bar, and y bar was a constant value for all of those points, correct? Because it was just the mean value. But right now, for each value, you have a prediction, which is this fi prediction by the regression line. So together, all of those distances, they form a vector, and the norm of that vector gives us a sense of the average distance of those points from the regression line. So just like we did with the mean value, we can now compute an average distance from the regression line. So I want you to go ahead and do that. Okay, be inspired by the formula we developed for the mean. So pull up your slides. You see what we did with the mean. Okay, and I want you to convert that sum yi minus fi squared into a distance. Okay, into a distance. Do you want to work with Brooke and Nathan? You guys form a new team. Over here, you can already a team together, right? You're already, that's your team. Good to have you back. Okay, Jake and the Jupiter Snakes. Okay. Hey, Hayden, you want to work with Lizzie? All right. You already know the answer. Ah, yeah, but no, it's not. Straighten him up, please. So remember, now we are measuring the distance from the regression line, not the mean. So that fi, okay? So that summation up there is the total distance, okay? That's the aggregate distance. We need to fix it to, it's a distance squared, really. So we need to fix that like we did with the mean value, okay? Do you guys want to work together? Yeah, yeah. Collaborate, talk, speak up, be loud. So that's going to be a fun discussion. What's going to go in the denominator? Okay. How's going, group name? Would you mind putting your name tag? Brooke, I know you. You don't need to put the, just so I get to know you. I've to get to know your name. Okay. Should be under the square root. You guys get anything? And under the square root. Okay. So we talked last time about the n-1, right? Yeah. So now let me ask you this. What is the spread of the data if you had two data points and you were to do a regression on those two data points, only 2 points? Okay, what is this? Is there a meaning for the spread of the data? So last time before we left off, I said for the mean value, actually we probably didn't discuss it in class, but one of your colleagues asked me. So for the mean value, you had n-1. I said because you already used one parameter. Another way to think about it is to say, what is the standard deviation for a single point? It's undefined, right? So if you plug it in that formula, it gives you infinity because you get n-1 at the bottom. So now, what if you had 2 data points? What's the spread of data around the regression line between 2 data points? Doesn't make sense, right? So all right. Okay, let's see. Okay. All right. The team way in the back. What was your team's name? Would you mind having your name tags up? I think yeah. Right. Do you guys have an answer? No. No. Pardon me. No denominator. Okay. Okay. Why not? N minus 2. Yeah. For large data points, it's not going to matter, but you'll see what it is. Okay. So who's got an answer? So the team, one of the teams didn't know and what to put in the denominator. So we need a square root around the summation to turn it into a distance, right? So to get rid of that square. Okay. That's correct. But you need to average that over all the data points. So we need to divide by n, or n minus 1, or n minus 2, or n minus 3, or what is the denominator, Maxime? Okay. Yes. Well, I don't know. Okay. Who sides? Okay. Forget that. Forget that. Quickly. Okay. Who sides with Maxime and who dissents against him? And you better back up your answer. Okay, Nathan. Oh, only Nathan sides with Max. Nathan, okay. Okay. So why is it n minus 2? So you said yes, we have the 2 degrees of freedom, which are no. Yeah, Nathan. Yeah, the 2 constants in the line, you already used the data to fix 2 degrees of freedom, which are A0 and A1 in the straight line. Okay, so you lost really 2 data points from your data. Another way to think about it, so going back to the mean value where we had n minus 1 in the denominator. Okay, so let me ask you this: what is the spread? What is the standard deviation for a single data point? It's undefined. It's kind of undefined. Well, you can say it's 0, but it's really should be undefined, right? So if you think about it, going back to the formula with the mean value, we had n minus 1 in the denominator. With a single data point, it gives you infinity, which is a nonsensical value. There's no spread of data around the mean value of a single data point. Same thing with straight regression to a straight line. What is the spread of data of 2 data points around a straight line? It doesn't exist. There's no spread of data. So we have the n minus 2 in the denominator to knock out that gives you an infinity for this standard distance. Okay, so the answer is n minus 2. All right, and we will learn later that that number in the bottom, that number over here, depends on how many parameters you have in your model curve. Whether you use the explanation, okay, Nathan gave, that we already use the data to fix 2 parameters or 3 parameters or 1 parameter, okay? Or use the explanation of like the spread of data around 2 points that is nonsensical. This is the correct answer, okay? Now, if you put n or n minus 1 for large data sets, it's not gonna make a big difference, honestly, if you commit that mistake, but rigorously, mathematically, this is the correct answer, okay? Now, I call this sy given x because I want to distinguish this from the previous error, which we called it sy, the standard deviation. And look, this is the square root. So it gives us the correct units, and it averages this in total distance over n minus 2 points. We call this the standard error. And you can think about it as the standard deviation with respect to the straight line or to the regression curve. That's what the standard error is. That's why initially I went back, when I first started this discussion, I told you to think of the standard deviation as the error in your data if you were to use the mean value to describe those data. Because I'm headed in this direction, because this, we call this an error, not standard deviation around the straight line. So instead, I'm going to call the standard deviation as the error committed in using the mean value to represent all your data. Okay, I'm getting somewhere. All right. So again, this standard error has the same properties. Okay, it has the same properties as the standard deviation. It's just it is identical in meaning to the standard deviation, but except of doing it with respect to the mean, you're doing it with respect to the regression line. Okay, it does represent the average distance that the observed values fall from the regression line. Okay, now there's a statement here. I say it tells you how wrong the regression model is on average. Okay, we're gonna quantify that. We're gonna discuss that a little bit more. Okay, so but that's kind of if the formal definition over here. Okay, now for these data, okay, I have some numbers here for you for the height versus femur. Okay, before we head to the next discussion. These are the height and femur data. The mean value is 167.8 centimeters, and the standard deviation is 164.7. Sorry, the standard deviation is 3.16. Never mind, 3.16. Now, if you put a regression line, SY was 3.16. Now SYX is 1.43. So if you think about regression as saying, okay, I'm going to use a model that is better fit to describe the data than just the mean value, by how much did you change that spread of data around your model? So if you were taking the mean value as your model, your error committed was the standard deviation, which was 3.16 centimeters. If you were to use the mean value as a model to predict your data. However, by using the straight line regression, okay, you reduce that error to 1.43. You change your standard deviation because you change your model. There are so many ways to spin this. So think of it again. The standard deviation, what we call standard deviation, if you are using the mean value to predict the data and describe the data, the error committed in that description is called the standard deviation. Okay, over here that was SY equals 3.16. Now I came in and I brought a new model for you called a straight line regression. With respect to that straight line regression, the data is spread around it according to the standard error SYX. And when you compare that SYX to SY, it's much smaller. It's smaller. It's probably it's almost cut in half, even more. Okay. So we kind of changed our model so that we've reduced our spread of the data around what we're using to predict the data. Okay. Now this naturally leads us. So when you compare those two, we can use them to estimate how well our regression is doing. And this leads us to the coefficient of determination, or the R-squared value. So who is familiar? Excuse me, COVID. Who is familiar? My pitch is stabilized, is regressing to the mean now. But so who is familiar with the R-squared value? Okay, so you've seen it. You kind of seen it, right? Okay, you've seen it. You've used it in Excel, etc. Did you study it like ever in depth? Do you know kind of exactly what it means, what it measures, how to describe it? You're sitting on the bus, you know, someone sitting next to you. What do you study? Oh, you know, I'm an engineer, and we're like doing a model regression for the data. And they ask you, okay, what is your R-squared? What do you mean by R-squared value? How would you describe that? Okay, so I hope the next slides will help you be able to answer that question, because they've helped me. I didn't know what the heck R-squared mean. Okay. So the standard deviation and the standard error can be combined to assess how good a data fit is. Recall that the standard deviation was the spread of the data around the mean or the error committed. That's the new thing I want to introduce to you about standard deviation. If you were to use the mean value to model the data, to predict it, your standard deviation is the error on average that you commit using the mean value to predict the data, okay? Now, from that, you know, I'm gonna take all of SY, I'm just gonna take that summation, call it S of T, okay? And that, I'm gonna call that the magnitude of error prior to regression with respect to the mean. We are always holding the mean to a very high standard as our like reference, okay? Because the question was, well, how do we really measure the error of regression in absolute sense? You can't. You always have to measure it with respect to something worse or better. So because the mean is the simplest statistic, we always take that to a high standard as our reference, as our gold standard. So from the standard deviation, I'm just gonna take that numerator, okay? You could have taken the entire square root, doesn't matter, but the mathematics become much simpler when you do this. So I'm gonna take that summation, that total distance from the data points to the mean, okay? I'm gonna call that the magnitude of the error prior to regression with respect to the mean, okay? Now, also we said that when you do regression, again, the data is spread around the regression line and it gives us this standard error. And from that standard error, I'm gonna take that numerator, which is the magnitude of the error after regression with respect to the regression line, okay? Now, remember the slide on the femur length and height. The standard deviation was like 3.14, and then it was cut in half when we did regression. Those are the same things here, ST and SR, okay? So this SR characterizes the error that remains after the regression. I'm thinking like, why did I put that statement? Because now it's like not very clear, I'm thinking. So forget that I mentioned this statement, okay? Forget that I mentioned that statement because it's gonna come clear on the next slide, okay? So now I want you to think of those two, the magnitude of the error prior to regression, and don't look at the slides to come up with the answer. I want you to try to come up with the answer to this question yourself because it's a eureka moment, okay? So the magnitude of the error of the data with respect to the mean is this S of T, and the magnitude of the error after regression with respect to the regression line is SR. Now together, the difference between ST and SR means something. Or think of it this way, the relation between ST and SR means something. If ST is greater than SR, less than SR, or if SR is greater than ST, less than ST, okay? I want you to take a moment. I want you to take a moment and attempt to explain that difference. The simplest way to do it is to think of is if ST is equal to SR, if ST is greater than SR, or if ST is less than SR. Okay, so ST is everything with respect to the mean value. Okay, SR is everything with respect to the regression line, and it's an error. Think of ST and SR as errors. So what happens if they're equal? If one of them is larger than the other and one of them is less than the other. Okay. Talk in groups. Kia, do you want to join group? And Nathan, Brooke and Nathan? Thank you.